the lab. It's maybe professors can really mention something. It's going to be some kind of interactive lab. You will be divided in groups. Then you will be assigned a problem, and you will have to cooperatively, solve this task. And there are some tools which is important that I mentioned before tomorrow, and this is the goal of this lesson. Okay, so together we will see basically some signal processing technique that you will probably need to use tomorrow in the lab. Does any of you already did this the last year? This lab? I hope you forgot. So, I mean, there's a slight difference, but in general it's similar. Okay, by the end of the lesson, I will give you the text. So we will give you the details to it. And this lab is basically about three things, which is first, it's about, among the things that you will need, one of those is time of delay estimation. Have you ever heard about time delay estimation? Okay, basically you have a signal, you send a signal, then you, depending on the signal that you receive, you measure basically the delay between the two signals, and this allows you to estimate the range. This is usually used in GPS technique and other position techniques. Then we will need to go through what is called MIMO. MIMO is multiple input, multiple output, and I would say that is the most used technique in today's communication system. Basically, it's based on the idea that you have multiple antennas of both the transmitter and the receiver, and this allows you to increase the capacity. Okay? So, time of delay estimation, MIMO, and then all of these are complicated by the fact that you will deal with very, very long sequence. Okay? Actually, you will deal with music, with sounds. Okay? And sounds have very, very long signals, so you will have to perform block processing. So we will also give a look at some block processing technique, which is okay. Let me start from this one here. Time of delay estimation. Let's start first from an example. Let us assume that. Okay. Let us assume that this is a highway. This is you with your car. Okay. And here you have the worst enemy of any driver, which is the speed detector. And the main idea is that the speed detector has to detect your speed, and if you go faster than below say, then you will be charged, or even your driving license will be taken away. So, do you have any idea how this works? How does this box here estimate your speed? It's based on time of delay estimation. There are several implementations, but one of them is based on time of delay estimation. So, let us assume that some time t1, this guy here is sending some signal, and this is the signal that is sending. Okay. Then the signal travels, the signal bounces here, comes back. And let us assume that you are at this moment at a distance d1. And then what you receive is basically a delayed version of this signal, okay? This is the time that passes between the signal that you transmit and the one that you receive. Let's call this part1. Okay. Now, how do I estimate this distance d1 starting from part1? basically, we know that the signal propagation in free space, the speed signal propagation in free space is c. I mean, it's usually not a c, it's 3 by 10 to the 8 meter per second. And so, you know that this d1 is actually equal to the time by the c. Well, actually, this is a two-way signal, okay? So basically, it's this time is the one that takes to make twice this distance. So then you can estimate d1 by tau 1 c over 2. Then you get closer, okay? So and the speed detector sends another signal at T2. And by this signal, you are able to again, you have the same situation. You estimate tau 2, and from tau 2, you are able to estimate D2. Now, basically, you can estimate the speed of the vehicle by asking yourself, basically, what's the distance that the vehicle, you know, did between these two time intervals? Okay. And this depends on c over 2. Let me define this as delta t. And then, of course, it depends on tau 2 minus tau 1. So, by this procedure, the speed detector is able to detect the speed. Now, the main problem is how can you estimate this delay here between these two signals? Okay, this is the main goal of this first part of the lesson. Try given a signal and given the same signal displaced in time to estimate of how much is this displacement in time. Is everything clear? Okay. Otherwise, you know, you can stop me and ask questions. Feel absolutely free. Now, so the problem is, I have one signal, G1, this. Then I have a second signal, the second signal is displayed by tau, and basically it's equal to the first signal delayed by tau. And now the question is, given signal G1t and signal G2t, how do we combine these two signals in order to get an estimate of tau? Does anyone know which tool you can use to estimate that time difference there? Okay. The tool that you can use to do this is called cross correlation. Okay, what the cross correlation does is actually exactly what we need. The cross correlation measures the similarity between two signals as a function of their displacement. Okay. It's very similar to convolution, except for the fact that you don't flip the second signal. You take the two signals, and then you start shifting one over the other And then for each one of these displacements, you measure how these signals look like each other. Okay. So the definition of cross correlation is basically you take one signal and you convolve the first signal with the second one, which is flipping time. This means convolution without the pre-flipping operation that you do in convolution. And this is the conjugate transpose, but we don't need it as these signals are real. So basically you take one signal, okay? See, this is exactly as convolution. The difference is that here the sign is plus instead of minus. Okay, so let's assume that this is the signal that we want to shift. Let me write here the results of that operation, which is the cross correlation. So here we have the cross correlation. So at this moment, which corresponds to instance 0, if you make element by element multiplication and then you sum, it's 0, right? Because this signal is not negative only in this portion here, where the other one is negative. Sorry, where the other one is 0, and this signal has some value only when the other one is 0. So when you sum up this, you end up with 0. Then you take this other one and you shift it, but it turns out that this is 0 until the moment when the first signal is exactly in the same position of the other, and that's the moment where they are more similar, okay? So in that specific moment, your cross correlation will have a peak, okay? And you know after how much time this happens? Tau. So it's pretty easy. You take two signals, you cross correlate the two signals, and then you take the maximum of the cross correlation, okay? This is basically the time of delay estimation procedure. Questions? Okay, let's go on. So you take Matlab, you take one signal, you take the other one, you use the function xcot, you cross correlate the two signals, you look at the cross correlation, and then you find the index which corresponds to the maximum. As simple as that. Can I cancel this one here? Okay. Basically, this is what we will code together after this introductory part. As simple as that, but things in reality are not as simple as that. Because ideally, what you have is a cross correlation, which is some very nice impulse, which in reality doesn't exist. What you have in reality is basically something that looks like this. You still have your impulse, but then you have your impulse basically has a shape which is similar to the one that I wrote. But not only that, you have sample signal, so you do not have access to all the information. You have access only to some few samples of it, okay? Because you sample signal. And imagine that you take this sample here, this sample here, this sample here, this sample here, and this one. So you do not even have this one here. What you have is this. So when you look at that, what you do, you take the maximum of the cross correlation and you pick up this point here, which for you is the maximum, and you estimate your tau as the index of the maximum. So what you're doing, you're picking up this point here, and you're saying, okay, I'm a great engineer. This is the time of delay estimation, or actually, the real one is there. Now, how do we solve this problem? Have you ever heard about parabolic interpolation? Okay, so do you know the main idea behind it? Okay, so the main idea is that you assume that this function here has some sort of parabolic shape. So what you want to do, you take the, okay, sorry guys, actually maximum was this one here. So you take the point that you estimated as the maximum, you take the point right before and the one after, and then you assume that these 3 points are part of a parabola, and you want to find that parabola, assuming that your parabola is exactly centered to the real time of delay, which in this example we denote by p. So basically then you will try to compute this distance here, and then you will tune your estimation, saying that actually the maximum is likely this place with respect to this one here. Now let's see how you can do this in practice. So let's denote this as alpha, which is the value that the parabola has corresponding to this point here, which we denote -1 because the one on the left of the one that we pick up as the maximum. Then you say the maximum is the index 0, and this corresponds to beta. Finally, so this is gamma. So when we take the reference as this, and this is the 0, you see that what we want to estimate is exactly this p, okay, which is the displacement from 0.
How do we choose this reference?
Well, you just take the maximum of your cross correlation, and then you assume that that is in point 0, and then you take the one right on the left and one on the right. In this, this is basically is arbitrary, but you do it this way because if you set it 0 at this point here, then you say that you see that the correction that you have to apply to estimation is exactly b. Okay, you can choose 2, but then it's just a convention because it makes things easier. Okay. And now, so basically this is your x, this is your parabola which is yx, and you assume that your yx is equal to something, okay, which is a parabola centered in P. Now what we have to do, we just have to solve that equation for the points that we have. So you basically find that alpha is equal to y in the point -1. Beta is y in 0, and gamma is y in +1. Okay, so you plot -1 here, and you find that this is a -1 minus p squared plus b. This is equal to a p squared plus b. it's very early in the morning, so please pay attention to this computation, okay? And finally, yeah, A1 minus B plus B. Okay, so this is like A plus 8b squared plus 2ab plus b. What's this? Similar. And then from this equation, we got the value of b, which is beta minus a b squared, okay? Now let's take one of these two, let's take this one here, and we have that alpha is equal to a plus ab squared. Okay, actually first is better. Sorry, if these are very similar, it's better to compute the difference between the first and the last equation, okay? Which is a minus a 0, ap squared minus ap squared 0, b 0. This is basically 4 ap. So once you, because also you see that here we have 2ab, so basically this is similar to alpha minus gamma over 2. So it's easy to solve in this way. Okay, so let's take this first one here. So alpha is equal to a plus ap squared. Let's plug alpha minus gamma over 2, okay? Because alpha minus gamma over 2 is exactly equal to 2ab, which is this term here, okay? Plus b, which is beta minus ab squared. Now, okay? So, from this equation, you can get the value of alpha, of a. So a is equal to alpha minus gamma over 2 minus b. Two alpha minus alpha plus gamma minus 2b. Okay. Now, let's plug this into here to find the value of p. So from that equation there, p is equal to alpha minus gamma over 4a. And here we have a is equal to alpha minus gamma divided by 4. Alpha plus gamma minus 2 beta over 2. This is 2, 1. And here it goes p. Okay, so this is the displacement with respect to 0. This is the correction that you have to apply in order to get that estimate. Now, how do you find these values, alpha, gamma, and beta? Well, you take the cross correlation, okay? And beta is the cross correlation which is computed exactly in the, beta is the maximum of the cross correlation, alpha is the value which is right to the left, and beta is the value which is right to the right. Okay, so you have these three values. You just, by taking the cross correlation, these three indexes, you plug them here, and then you find p. Okay, then you take the estimate, then you first estimate, and you correct it by that value. Is it okay? I mean, this is a technique which is quite common in this kind of application where you have to pick a maximum that you degree of point. You will probably see it in the next lessons, but it's also used in frequency estimation, which is a topic which is very important for this course, and I'm very sure Professor Spagnini will devote some time to it. Okay. Let's see, what else? I mean, what we will do next, we will generate a signal. We will display the signal by some delay tau. This is our way to generate our synthetic data, and then we will measure the delay between these two signals. Do you know how to displace a signal? Given a signal G, you know how to get a signal G2, which is G1 displaced by tau. Oh, shift. Yes. Shift. Okay. You can take the signal, you can shift it, but in this way, again, you're a little bit, constrained to this sampling here. Basically, you can shift by an integer number of samples. Otherwise, you can do it in frequency domain. Okay? Because you know that time shift in time domain is like the Fourier transform, which is multiplied by a complex exponential. That's one of the basic, signal theory technique. Okay, so let's give a look at this because there's some implementation details I want to discuss with you before approaching the frequency domain in Matlab. And it's basically due to the fact that Matlab doesn't have the notion of negative frequencies. Okay, you take a sinusoid, you look at the frequency domain of the sinusoid, and you expect to have these nice pulses, which one is at the negative frequencies and the other one at positive frequencies, right? This doesn't happen in Matlab because you don't have negative frequencies in Matlab. So is it okay? Well, let us assume that you have a frequency. Sorry, you have a sinusoidal time domain, which we call xt, which is 2, 5, t. Okay. This frequency, this sinusoid, of course, is a sample. So basically, this is correspond to a discrete time index, and which is divided by your sampling frequency. Let's call this f0. Okay. So when you have a sample sinusoid in a discrete world, which is the one we are representing using Matlab, is f0 over fs by n. So the ratio between the frequency and the frequencies that you're using, the sample frequencies, is also called normalized frequency. So let us assume that our normalized frequency is 0.1. You take the Fourier transform of that sinusoid here. This is 0. This is minus 1/2, and this is up 1/2. And what you expect is to have your okay. So do you know what happens if you implement the Fourier transform of this method? What it does, since it doesn't have the notion of negative frequencies, okay, let me use like negative. frequency, and this is the positive frequency. Well, Matlab, what it does, it takes the positive axis and it puts it first. Okay, so when you look here, and this is your, let's say, Matlab window, Matlab signal, the positive axis is first. Okay, so what you see is something like this, because Matlab takes the positive and this is the negative frequency. I mean, this is done in such a way so that the index 0 in Matlab corresponds to the real 0 of your frequency axis. So imagine you want to take the maximum of that function there, and then you have your signal in such a way that the positive axis it comes first in your frequency domain vector. Okay. I mean, it's just again some convention. You just need to pay attention to it. So the reason to solve, I mean, the way you can solve this is either by using a built-in Matlab function, which is called FFT shift. What it does, it automatically flips back these two signals. Or the other possibility is to define your frequency axis starting from 0 to half and then from minus half to 0. Okay, basically you flip either your signal or your frequency axis. Okay, said so, I think we can probably start implementing something. So let me just write down. Oh, it is not smart how this is placed in this language. I will have just some. Okay, I will try to write everything here. Okay, this is something that we will need when we will shift in frequency domain the signal. Now, what we will do is the following. We will make this time of delay estimation by assuming that we have a long sequence. So what we will do, we will take block of this sequence from the block number 1 to the block number n, and we assume that each one of these blocks has n samples. We will just do exactly the cross correlation things I told you before, but just in a blockwise fashion. So we will have n, which is equal to 5,000 interval, n is equal to 256. So we will take one. This is, let's say, the sequence G1T. In the code, we will display this sequence by tau samples. So we have this. Then we will have to generate the second sequence, which is G2, which is basically D1 displayed by tau. We want to test this algorithm for different values of tau. I'm running out of space, so okay, tau, it goes from 0 with the step 0, 1 until 1. These are samples, okay? And of course, the performance of this always depends on, I mean, we will not have access directly to the signal. We will have access to this signal plus some noise, as always. Okay? So, still, we will have to define some SNR, which is the ratio between the power of the signals that we want to cross-correlate and the noise, which is affecting those signals. And we can make it from 10 to 40. I mean, remember last time what we did, it was to make the channel estimation procedure by taking, let's say, one situation and say one picture, one channel, one data, and then making a for loop over a lot of different iterations. What we do here is a more realistic situation where this loop is over basically the same signal, which is very, very, very long. Okay, it's similar.
Sorry, I don't understand how we define the signal to noise ratio.
Okay, each one of these two signals, which is
okay, so that number is for each signal.
yeah.
Okay.
We will use the same signal to noise ratio for G1 and G2. We have two signals, they have the same quality signal, and then we will try to cross-correlate these two signals in order to get the peak. I mean, the main idea is that if you have two very, very nice and clean signal like this, you cross-correlate them, you will not get exactly this peak, but something which is very similar, okay? But if this is very noisy, okay, what you will get is like other peaks. And it's likely that this noise will generate an additional peak, which is not due to the function itself, to the signal itself, but to the noise. That's how the noise is basically impairing this procedure. Okay. So we define the SNR. Let me check if we need something else. Okay, we will also compare this with the camera bound. Okay, for this kind of, I will use the camera bound only as a benchmark, okay? For this kind of signal and this kind of processing, computing the special camera bound is possible, but it's a little bit tricky, so I will just give you straight away the equation for the camera bound, which is a little bit complicated, but we don't need to know. I mean, of course we can compute it, but it's out of the scope of this specific example to show you how to compute this. Just let us assume that the camera bound is okay, and I don't even know it, of course. So this is 3 over 8 by n by t squared. This BF is the effective bandwidth of the signal. It depends on the bandwidth of the signal that we're using. This is the SNR, and again the SNR. Again, you don't need to know details about this. I just want to plot it and just to see how good or bad our estimation is. I think I'm done with this phase of the blackboard. So. I think we don't need anything else. Just for me, the model for the signal G that we will use is just arbitrary. What we will do, we will just take some random noise, and we will filter this by some filter. Again, you don't need to know details about this. It's just called Butterworth. And we will need to feed this block just with the model of the filter and some bandwidth. Again, details are not really necessary, just an arbitrary signal that we are using. It's usually used for these kind of applications. And we use a filter with order 8, and the bandwidth is 0.05. These are just parameters that we will need when we will implement this. And then the last thing we need is, just as a reminder, to know the displacement I showed you before, the parabolic interpolation, the correction term that we need to apply to our estimation, which is let me define it as C, the cross correlation at point -1 minus C plus 1 to C minus 1 plus C plus 1 minus 2 C and Z. Okay? This basically corresponds to the alpha, beta, and gamma, which I defined before. Okay, I think we have everything, and we can. Okay, sorry, I left the copy first. Well, in principle, this should not cover the. I don't remember how it. P is P, right?
Yeah, it is P, but I don't know why P. I mean, there is something.
Because it's a delta T, okay? You have the x-axis with the t-axis, so that displacement is some, some additional delay that you output. It's a delta delay.
So it's not a differential term.
No, sorry. Let's call it P, sorry.
Okay. Thank you.
You're welcome. This class is not well designed. Can you all see the screen? No. Sorry. I mean, not the other part of the blackboard.
If you just turn off some lamps and
Yeah,
set the
sure.
curtain down, that would be better.
Okay. Is it okay? Do you want to switch some other light? This is dangerous. I mean, we will definitely fall asleep. Okay, is it okay? I cannot switch off more than this, otherwise I will fall asleep. Okay, now, looks like there's a problem with this.
You cannot register the firma.
Sorry guys. I think I have to duplicate the screen. Okay, this is weird. Okay. Okay, let's start. So, let's first, as always, start a new script. This is going to be a time of delay estimation. let's start with some of the parameters that we have there. For those of you that cannot read, we have 256. This is the number of samples per interval. We have 5,000 intervals. Okay, this is just an alternative way of writing 5,000. It's like 5 plus 3 zeros. And then the n tot number of samples, which is the total number of samples that we have, is just the product of n by n. This is the total number of samples. Okay, now we need, as always, the SNR minus 10. Let's say step 5. And this is the SNR in dB. Okay. As always, after defining the SNR, what you do, you usually, after defining it in dB, what you do, you usually convert it in a linear scale. Okay. I mean, as these are things that we already seen last time, I'm going a little bit faster on these, but anyways, if you have any questions, just stop me and I will detail more. So this is the linear SNR. Then we have to define the tau. Okay. Basically, I define it as a tau vec. It collects all the different values of tau that we will test for our algorithm. So this goes from 0 to 1. Tau. What else do we need? We will need to generate the signal, which is the G. So signal generation. As I said before, I mean, it's not important how we generate the signal, it's just the signal we use for this code. So we take a random noise. Random noise. This is a Gaussian random noise with power 1, bias 1, and 0 mean value. And then we will filter this by a filter which is called Butterworth. We can implement by using this function, and we just feed into this function the filter order and the bandwidth, which just as a convention is defined as only the positive one, so you double it, okay, before plugging into this. So this is the Butterworth filter. And we said that the order is 8. Filter order is equal to 8. Bandwidth 0.5. Okay. Again, just a signal. Positive. Okay. Is it okay? Now, what we do, we have to filter the noise by this filter, and you can, you can use this by the function filter. So basically, you take filter, you put your coefficients, and then you filter by W. So this is noise filter. Okay, should be okay. I mean, this is a function that I don't know if you know it, but you can use it. Let us assume that I will give you some signal, and I will tell you that this signal is controlled by a sequence, and you know only the Z transform of the signal. Basically, you know the coefficients of this filter. What you can do is just to plug the coefficients into this equation, where B is the denominator and A is the numerator. I think, otherwise check help in Matlab, but I think it's like this. It may be the opposite, but anyway, you plug the coefficients here, and then what this function does, take your signals, okay, and it filters the signal by these coefficients. This is something that you will have to do in the very first exercise of tomorrow lab, okay? I will give you a signal, convolve with the filter, and I will give you the filter. You have to deconvolve it. It's like the step 0 of the exercise. Okay, now, what else do we have here? I think it's okay. Now we just have G, which is the signal without delay. No delay. And then what we will do, we will make a full over tau, and then we will have to displace a second signal by tau. And to do this, we will do it in frequency domain, okay? Basically by multiplying the Fourier transform of G for a complex exponential. So what we will need is also the Fourier transform of G. So this is the FFT, which is the Fourier transform of G. Now, as I said about the frequency shift operation, it is important to define a frequency axis, which is also flipped by this frequency shift that Matlab does. So in this case, we can define a frequency axis, which normally it should go from minus n tot over 2 plus 1 to n tot over 2, okay? But this is how we expect it to be. What we have to do is to basically modify this in such a way that the positive comes first. So actually this should go from 0 to n tot over 2. This is the positive, which we are basically, so what we are doing, we are taking, this one is made by negative, by a positive values. We are taking the positive values and putting them first, and then taking the negative ones and putting them at the end of this frequency axis, which here goes from minus n tot over 2 plus 1 until minus 1. Okay. Now this is exactly as taking the FFT shift of this. Okay, this is exactly the same operation. So we just take this one here. Okay, this is just to face that implementation detail of Matlab, which does this kind of operation in order to let you have the frequency, the positive frequencies at the first part, in the first part of the class. Okay. Now I think we can start the loop, and we can do this by okay. The loop is over tau values. Okay, so we start the for loop. Tau is tau vec of a tau. Select value of tau. Now, once we have the value of tau, what we need to shift the second sequence. So we define G2. We take G, and we multiply G. By the way, every frequency domain operation in Matlab is performed element-wise, element by element. Okay, so you take the frequency Fourier transform of G and you multiply element by element of this complex exponential. So here is where it comes, this notation here, which is element-wise multiplication. So this is a complex exponential, which is this is just the J usually. This. I mean, you can also define it by I, but then Matlab will tell you why don't you use like this. So we do it. To pi, then we have tau, of course. Then we have our frequency axis that we defined before, and this is normalized by the number of samples. Okay? This is just multiplying a frequency Fourier of a signal by complex exponential. Is it clear? Then we need the time domain signal, so what we will do, we come back to the time domain. But first let me, so this is basically a delay in frequency domain I mean, the main reason why we are doing this is that if you do in time domain and you just take the signal and then you move it in time, then you can do this just by integer, values of tau, because that's the sampling that you have. So in this case, you can plug here arbitrary values of tau. And then we come back to the time domain. So time domain. This is the inverse fast Fourier transform, and we need just the real part of it. Okay, so we have the two signals. Now, what do we do now? We can first define directly the noise, which will be impairing these two signals. So we define a noise vector. Look, we are defining the noise inside the loop because we are defining the noise for the overall duration of the signal. So we are directly defining the noise for n tot samples, which is like basically all those samples over there, okay? So basically this is the noise for the overall signal duration. As I said, when we were doing channel estimation, we were generating the noise inside each Monte Carlo loop. But now what we are doing, we are generating a signal, such a long signal where this averaging effect is done by the fact that this signal is actually very, very long and we have multiple intervals there. So basically, of course, the noise in each one of these intervals is independent on the other interval. Okay. This is basically more realistic because in reality what you have is, imagine some real-time signals and then you just sample, basically you window, that's the technical term. You window the signal, you take one portion of the signal at a time and then you process that part of the signal. That's what we are doing there. Okay, now we loop over SNR values. Okay, differently from what we did last time, it's just the same. It doesn't change anything, but what we are doing here, we are keeping fixed the power of the noise, and what we are doing, we are basically scaling the power of the signal, okay? You understand that in the end, the ratio between the power of the signal and the power of the noise, which is the signal to noise ratio, it doesn't change. You can either scale down or up the noise or the signal. Now we are defining the noise, we are fixing noise to the power of 1, and then we are scaling the transmit signal. So here you have signal x1, which is G1 plus W1, and now we need to scale this by the SNR values of this iteration, okay? And x2 is the SNR. Okay, so these are signals G1 and G2 plus noise. So we have the whole signal and dot samples. Now the next step is to take the signal block by block, interval by interval. Okay, so we start for loop over intervals, which is yes. Okay. Now what we have to do, we have to take the first, at each of these IN iteration, we have to take exactly that specific portion of the signal, whose length is n. Okay. So basically, we take x1, but only some indices, and x2, and again only some part of it. Now, which indices do we take? Well, this is a common way of addressing some specific portion of the signal, but what we can do, let me first write it down and then I will spend a few words on it. You can basically take the index you are looping over, which is IN, okay? Subtract -1 multiplied by n plus 1. This is your first index, Okay, and you can see that at the first iteration, this is equal to 1, because IM is equal to 1, 1 minus 1, 0, 0 by M, 0, so this is exactly 1. At the second loop, this IM is equal to 2, so all these things will be N plus 1, so you're taking the second blocks and so on and so forth. And then you go up to IM by N, okay? So first iteration from sample 1 to sample N, second iteration from sample N plus 1 until sample 2 by N, and so on. We are slicing our window and selecting at each interval the portion of the signal we're interested in, okay? In any block processing technique, you will see some addressing like this. So we select exactly those indexes at each iteration. So these are the indexes of EM block. S1 and S2. Now, I'm sorry about the fact that the Windows is still shrink, but okay, now we have our two signals. Now what we have to do is to cross-correlate these two signals, okay? So we find the cross-correlation. We define it as C, which is the variable that I use there, and C is the X-core between X1M, X2M. And then we take the maximum of these. This is, the function max will give you two outputs. The first one is the value of the maximum, and then the index, which corresponds to the maximum. This one is just used to say, I don't care about the first input, I just need the second one. So we take the maximum. So basically, in principle, this is exactly what we're looking for, okay? And so we save it in tau estimate, which now is at iteration M. Okay, let me now define here this tau s is equal to 0 and 1. Sorry. Now again, when you take the cross-correlational signal, again in Matlab, what you get your cross-correlation function can you see it? Okay. Your cross-correlation function, again, it will have some negative axis and positive axis. So this is for you is yes, okay. This is tau, but then actually you have 0, which is negative axis and positive axis. And so when you estimate tau, actually you have to take in mind that Matlab start addressing from 0. Okay, so what you have to do, you just have to shift it back once you get tau. So basically you take tau and then you shift it back by n samples just to take, to get rid of the fact that Matlab actually doesn't account for negative samples. Okay. Because otherwise, if you just take that ED max, what you get is, this, which has here n samples. Okay, this is why the cross correlation of the signal, which is n, is again n plus n minus 1, which is the same as correlation. So the overall sequence here is 2n approximately, and then since these are negative, you shift it back by n samples. This is just to motivate the fact that what I wrote here in the code is actually wrong. You have to shift this by n samples. Okay. This is again due to the fact of this notion of negative time and negative frequency, which is an abstraction that is used to explain concepts, but in reality doesn't doesn't exist.
What is the dimension of tau s and of the vector?
It's m.
Right?
Yes, we're estimating a value of tau for each value of m. So basically you shift, and then for each window you estimate tau there. I mean, the idea is that if you take a big signal and you shift it, then when you look at the signal window by window, in principle, the tau is the same for each one of these. So what we are doing, we are basically estimating it m times and then averaging over these m blocks. So we estimate tau like this. Now we have to apply the correction, okay? So the correction is there, we said it is P. So, okay, let's define first the numerator, which is C. Let me copy this just to make it quicker. E minus 1, right? Minus C plus 1. This is the numerator. C minus 1 plus 1. Then you have the denominator, which is twice C minus 1 plus C plus 1. And then minus 2 times C exactly at ED max. Okay. I mean, Matlab, you can use this when the line is too long, just to go. Okay, now we have P, which is nu over denominator. Okay, actually, this should be done before the estimation, so let me just move this after. So this is the parabolic interpolation. And here we are adding our correction term P. Okay, I think we are pretty much done. What we have to do now is just end the cycle. Okay, we have to compute the error, which we do it here. Okay, if you do like this, you see which 4 cycle this n corresponds. So here we are finishing the loop over the blocks, the intervals. So here we are inside the 2 cycles, which is the SNR and tau. So what we make, we compute the MSE for each SNR value and each tau value. Okay, first we need to compute actually the error, which is tau estimate minus the real value of tau. So we compute the error, and then we compute the mean square error. As the last time, this is done by taking the away the row column product of the vector and divided it by the number of samples that it contains, which is m. Okay, each for each interval of the signal. Okay, what's going on here? Oh, we haven't defined the MSE. Okay, sorry, I will have to copy this and then I will. Okay, so define the MSE. So we have the mean square error, and we want a number of rows which equals the length of the SNR vector, and the number of columns which equals the tau vector. Maybe you can, okay. Okay, now, we just need to plot the results. Well, actually, we need to define the camera bound. Okay. I cancel the camera bound. Where is it? Okay, the camera bound should be 3 over 8 by n by, again, don't need to know, I mean, this is just some bound that we are using to see how good it is or bad. Then we have, this is, I call it, it was BGF, right? Which is the effective bandwidth, which was, again, 1.1 is just due to the signal that we are using. The characteristic of the transmit signal is not something you are asked to know. 3. This is by 1 plus 2 the SNR. And all of this is divided by the SNR square. Okay. Now we plot the results. Figure 1. Again, we plug in semi-log y. We have the SNR. I call it, okay, I just call it SNR. And this is the camera bound, well, MSC. Then we plot the camera bound and anyway, if we are measuring delay, which is in time, okay, so the parameter we want to estimate is the delay. What is the unit measure of the MSC? Yes, second square, which physically doesn't make that much sense. It would be nicer to have, you know, the MSC in a second. So what you do in this case is to compute not the MSC but the root mean square error. Okay, so basically you take the square root both of the camera bound and of the MSC. This is also used when you are measuring the error in distance. You don't want to have like square meter. So okay, so X label, we have the SNR. And is the root mean square error. Okay, I think this code is quite slow, so probably it's better to make some, to display something to know like where we are, and not to let you here waiting. So we are this SNR and tau. SNR, SNR, and tau. Okay, I cannot really say if this will work. I mean, we will just try, and then we will go through a very nice debugging phase. Okay, what I'm not sure for sure is that at first it's probably better to evaluate this just for, just for some values instead of waiting hours, and that maybe it doesn't work. Perfect. Okay, what's going on here? The problem is 939. I guess, I'm not sure, but I guess that what I'm doing is taking G, which is a column vector, and then taking this, which is a row vector, okay, and the old version of Matlab, it uses to tell you that you did something wrong, which is the matrix dimension, the vector dimensions don't match. But now they thought that they did something smarter, and they automatically, take one vector, extend it to the version of the other. So in the end, even if the dimension don't match, we get a huge matrix, which is something annoying for debugging. But in this case, we have been lucky because it turns out that this operation is too computationally demanding for my PC. So I figured it out, and then what we have to do, we just take this frequency and we make it a column vector as well. Okay. Okay, at least it's working. We have 40 SNR values for 2 values of tau. Okay, it works. Now, so we did it for tau equal to 0.1 and tau equal to 0.5. So which one do you think is the blue line and which one is the red line? Okay, the blue one is 0.1. Okay, and the other one is 0.5. Now, the yellow one, okay, maybe we can add a legend just to make things clear. Just for the, no, okay, legend will be a mess because it will have a lot of, so what we can do maybe is just to add a legend for the camera bound. Just to let you know which one is the camera bound. No legend. Extra comment here. No legend. Okay, legend. Okay, so again, the behavior is a little bit strange, right? This is due to the fact that we are actually making a non-linear estimation. I mean, when you have a function, you take the index which corresponds to the mass. That's inherently some nonlinear estimation. This will be, I think this is a topic where Professor Spagnini will spend some time when he will discuss about frequency estimation, which is another nonlinear estimator, which is basically based on some similar principle. You will have to take the maximum of some function. But again, what you see is that of course, the greater the SNR, the lower is the Kernel bound, which means that you get a better estimate. And also your estimation, like after some initial step, it starts matching the Kernel bound. Now, since this is non-linear means that you have some continuous function, which is the cross correlation. You want to pick the maximum, but actually you do it like at some discrete times, which are the samples. Now you made some trick about parabolic interpolation, but it's still an approximation. So when you increase a lot the SNR, meaning a lot, when you have only like almost zero noise, you have no other impairment, no other error, the precision that you get is just due to this approximation. So at some point, this will not decrease without any bound. At some point, as you can see here, your estimation will have floor, which means you cannot do better than this due to this approximation to this nonlinear estimation. Okay, I mean imagine like it's okay. No, it's not okay. Okay, okay. Let's assume you don't make any parabolic interpolation. Okay, so basically you know that your samples in time are displaced by some number of seconds, of microseconds. Okay. And then you want to estimate the tau, which is in the order of nanosecond. But, well, I mean, you're taking the maximum of the autocorrelation, so what you can measure, you can take a sample, which is, I don't know, some time, or maybe you can take the next one, which is displaced by a millisecond. Okay, because that's the sampling time that you're using, right? So, I mean, it doesn't matter if you cannot, by by taking a maximum corresponding to samples which are displaced by a millisecond, it's really difficult to get a precise estimating something which is a nanosecond. So in the end, when you have when you don't have any noise, you will try to estimate this, but there will be always some error. Okay. So as far as you have some noise, you have some performance which is driven by the noise. So it gets worse, it gets bad because you have some noise. When you don't have any other impairment, basically you achieve the best that you can do. You achieve the performance limit, which in this case are determined by this fact that the signals are deterministic, the signals are sampled, and the sampling frequency cannot be too much high. Okay. And also the sampling frequency, it's in digital communication system is the main one of the main cause of complexity. So basically, if you want to buy some analog to digital converter, if you want to get a very, very high sampling frequency, meaning that you will have very, very small displacement, you will have to pay a lot. I mean, the same holds if some of you if you like hi-fi music and analog to digital conversion is always some critical parameter, this, which is again the main cause of complexity, so money basically. Okay. Do you have any questions? Maybe you can give a look to what happens if we do not apply the parabolic interpolation. Okay, just to have an idea of how we are improving our estimate. So, okay, we will, of course, I will never remind that I did this, but just for now, let's set P to 0. Okay, in this case, we are not using the parabolic estimation, parabolic interpolation. So, what do you expect? You expect this floor to be much higher than before, right? I mean, let's see, but this is the main idea. By the way, this is way more sophisticated and complicated than what we will have to do tomorrow. Okay, I mean, we did a wall simulation with signals. Okay, you see, now it's evident, it's apparent that this flow effect will have to some limit, and then due to this.
So can you write in the code where you initialized the MSC, please?
Sure.
At line, I think 35 or 36.
36. No, the MSC, you mean the mean square.
Where you initialize the MSC.
30.
Here. Initialize, sorry. Here, yes.
Okay, thank you.
Go. Do you have any questions? Or maybe too much questions? Hey, the main idea behind this is that you take a signal, you take the second one, and you estimate the delay. If the signal is too long, you have to split your signal in different blocks. So you estimate the delay in each block. And then you take the estimated delay in each block, you average all of them in order to get better accuracy. I mean, imagine you have an infinite signal. The number of estimates of tau that you have, the amount of your prior data that you have, this is huge, so we get a better estimate. This is basically the same that we discussed when we were doing the channel estimation. If you have a very, very, very long train sequence, in the end you will get some better estimate. And this is basically reflected in the fact that okay, let's give it to the camera bound. Again, it's a little bit more complicated than the one from channel estimation, but again, you see that it scales with the SNR squared. You have also SNR here, but approximately this means that this scales down with the SNR. So if you have very, very high signal to noise ratio, then the camera bound will be lower. But what is interesting to see is that more than the number of intervals that you have, what really matters is the number of samples that you have in each interval, right? Which is this n here. Okay, you will see this later in the class, but basically when you decide to window some signal to take some specific portion of the signal, then there will be a trade-off between the length of the windows and the number of windows that you will use. Okay, and all of this information can be basically noticed, appreciated by looking at the camera bound. Okay, this is it for time of delay estimation. If you have any questions, otherwise I think we can reserve a break.